Hey Geometers, welcome back to another video lesson with Mr. Forster. Today we'll be going over Unit 8. You'll notice that the lesson numbering scheme has changed slightly. So we're going to be doing Lesson 8.0, which is a mixture of a few different sections in the textbook. But we're going to be going over dilations and similarity today. So let's go ahead and get started. Before we dive into the new information on dilations and similarity, your warm-up, which I want you to try on your own, is to find the image of the point X after it's been translated 4 units to the right, reflected across the y-axis, and then rotated 180 degrees about the origin. So here I want you to pause the video, and then I'll walk you through my solution. All right, first I'm going to plot our point X in blue at point -1, 5. So it's going to be from the origin left 1 and up 5, or right about there on our graph. Next, we're going to translate this 4 units to the right. So the colors of the boxes around what transformation is being done is going to tell me what is shown up on the screen. I'm going to go from that original spot in blue, and when I slide it over to the right, it's going to end up on that orange spot. Normally I would have a little prime symbol on there, but I forgot to add that to the animation, so we'll have to just make do without it. Next, I have this reflection across the y-axis. Just a reminder, the y-axis is that vertical axis going up and down. So I'm going to have my point there, which was orange, now it's highlighted in pink, and then it's going to go across the same number of units to the left of the y-axis as it was to the right. So because the orange point there is 1, 2, 3 units to the right, the pink point, which is the reflection, will be 3 units to the left of the y-axis. Next, I'm going to rotate this about the origin. And so the origin, let me grab my highlighter here, the laser pointer. The origin is that spot right in the middle. And so right now I'm over 3 and up 5. And so if I rotate this thing, I should be along a line that passes through the origin and on that same spot on the other side. So it should be the same distance from the center, and it should be on a line that goes right through the origin. The rule for this algebraically was to multiply both the x and y coordinates by -1. And if I was to show this visually, it's going to rotate around and land on that spot that is now 3 to the right rather than 3 left, and 5 down rather than 5 up. So I end up in this spot down here in the 4th quadrant. On to a few definitions to start things off. A dilation, which some of you may have heard this phrase before in mathematics class, you may have heard it just in everyday speak, is to enlarge or reduce by a scale factor. We call this scale factor the k value, and so we give it this denotation of k. And there's a few things that happen if my k value is certain ranges, particularly if k is greater than 1, then my dilation is going to be an enlargement. It's going to make my figure or my object larger than it originally was. Conversely, if my k value is less than 1, then the dilation is going to be a reduction. It's going to make my shape smaller. Here in part 3, we're going to find the scale factor, again, which is called the k value, and we're going to identify the center of dilation for each of these dilations that are given in the figures below. So in parts A, B, C, and D, we're going to be looking at these images and pre-images. Just a reminder, we have these little tick marks. That means that's going to be our landing spot or our final destination here. So it has a little prime symbol, a little tick mark there. That means that's the final image. And the pre-image is going to be the point that does not have the tick mark. So in part A here, we're going from this smaller object out to this larger object. And so I'm going from a distance of 8 from C out to point P to a distance of 12 from C all the way out to P prime. So C in this case is our center of dilation, so that's this spot right here. So that's identifying the center. We've done that here. And if I want to find what the k value is, well, I can take the values of these distances and I can compare them. Since my object is growing, and I know this thing is going to be an enlargement, I should know that my k value should be greater than 1. Now if I compare my image, my final image, this length of 12, which goes from my center to the final image, if I compare that to my original, which is 8, then that's going to give me my scale factor. I'm going from 8 to 12, so I can take the 12, which is my final image, divide it by the distance that corresponds to my pre-image, and if I simplify this, I would get a scale factor of 3/2. Here in part B, this time, if we notice, the original is the larger paperclip here. It doesn't have the little tick mark on it. The new shape is the smaller paperclip here. That's a little prime symbol, a little tick mark there. So in this case, I'm going from 30 to 18. So I know I'm getting smaller. I'm going in this direction, getting smaller. So that means that I'm going to compare this distance C to P prime is going to go on top, and then the original is going to go on the bottom. So in this case, I would have the 18 as the top value of my scale factor, and 30 is going to be the bottom value. And if I was to simplify this, 18 over 30 are both divisible by 6, so that would be 3/5. All right, I've shown you A and B. I want you to try C and D on your own. Please go ahead and pause the video right now. Let's go ahead and take a look at part C here. So in part C, again, we have our original is in blue here. It's the P without the little extra symbol up here, that tick mark. P prime is now smaller, so that means I'm getting smaller, I'm shrinking. So in this case, I want to look at this distance here, C to P prime. That's going to be my top value in my ratio or my comparison. So 4 is going to go on top, 12 is going to go on the bottom. So that means my K value, if I was to simplify this, 4 and 12 are both divisible by 4. So simplified, this would be 1/3. And finally in part D, this time we're actually getting larger. We're going from P again to P prime. So again, from blue to red. And so I have this distance of 10 is my smaller distance, but I want to compare the larger distance on top because I'm getting larger. So that's going to be my top value is the entire length of 25. So I'm going to have 25 on top. And then I'm going to have 10 on the bottom. So again, C to P prime is going on top, C to P on the bottom. And if I was to simplify this, well, they're both divisible by 5. So I believe that's going to be 5/2. You may have noticed I left each of these in fraction form. So I recommend getting used to doing it this way for 2 reasons. One, it helps you just practice with fractions, which is never a bad thing. And 2, it also is going to make some of our later concepts a little bit easier to navigate, and it'll make more sense if we keep it in fraction form later on. And I'm totally okay with these being improper fractions. I don't need these things in a mixed number. All right, in part 4 here, it asks us to list the coordinates of each figure below and then determine the rule. So just a reminder, an algebraic rule for some form of transformation is we're going to describe what's happening to our coordinates, x and y, and kind of generalize what's going on. So let's look at the coordinates of our 2 figures and see if we can come up with a pattern. So if we go over to our graph over here, we're going to plot points A, B, and C, or we already have them plotted for us. So in the case of A, if I go over 2 and up 1, that would be the point 2, 1. And then B, I'm over 2 more, it's still up 1, so a total of over 4 and up 1, so that's going to be the point 4, 1. And then C is also to the right 4, but then it's down 1, so it's going to have the coordinate point of 4, -1. And then if we look at our prime figure, our image, after we've done our transformation, or our dilation in this case, we have A prime, B prime, and C prime. If I go over to A prime, I'm over 2, 4, and up 1, 2. So the point 4, 2. And if I look at B prime, I go over 2, 4, 6, 8, and up 1, 2. So I have the point 8, 2. And finally, C prime is over 2, 4, 6, 8, and down 2. So I have the point 8, -2. So the pattern that's taking place here, if I look at each of these, I'm going from 2 to 4 and 1 to 2. 4 to 8, and 1 to 2. 4 to 8, -1 to -2. So it's not like our translation where we can just add values. It's more like our reflections and our rotations where we have to multiply by some value. And in this case, because our shape is enlarging, we're multiplying by our value of 2, which is also conveniently our scale factor in this case. So if you notice, if I multiply x by 2, I get 4 in my final image. If I multiply y by 2, I would get 2 here. I can follow that same pattern for each of these points. So each of the coordinate points, the x and the y coordinates, are being multiplied by 2. So when we talk about the generalizing, or anytime I talk about this coordinate rule for a dilation, I'm going to take the scale factor, which is our k value, and we're going to multiply that by both the x value and the y value to get our new image after we've applied this to whatever the coordinates that we have. If I have a single point like this, which is at x, y, to get to my new image, I can multiply that by k in the x position as well as k in the y position. So my rule is I take x and y and I multiply each of them by k for those coordinate points. All right, here in part 6, it asks us to graph quadrilateral KLMN with the vertices listed on the screen, and then its image after a dilation with a scale factor of 1/3. So let's go ahead and take a look. I'm going to go ahead and start off with plotting our different points. So at -3, 6, I have k. At 0, 6, I have L. At 3, 3, I have M. And then at -3, at -3, I have the point N. So if I fill things in using a straight edge, I get this nice quadrilateral here. And I know the scale factor is 1/3. So based on our previous slide, I can take the different coordinate points of each of these vertices of my quadrilateral, and I can multiply their x and y coordinates by 1/3. So that's what I'm going to do in my table off to the right here. So k prime, if I take -3 and 6 and multiply each of those by 1/3, I get -1, 2. For L, I have 0, 6, multiply each by 1/3, and I get 0, 2 for L prime. For M prime, I get 1, 1 after multiplying 3 and 3 by 1/3 each. And then similarly for N prime, I'll get -1, -1. And then connect all of my vertices with the lines, and here is my new image. All right, some word problems for number 7. In part A, it says on Microsoft Word, you change the font size from 0.5 inches tall, or half an inch tall, to 1.25, or 5/4 of an inch tall. What is the scale factor of this dilation? So the scale factor, which again we use the variable k for, letter k for, I can take the image length, so that's my final landing spot, and if I divide it by the pre-image, my starting position's length, then that's going to give me this scale factor. And I can apply this to any context. If I know what my ending length is going to be, and I know what my original length was, I can find my scale factor. So using this, if I plug the values in, 1.25 inches is my image length. That's my final length after I've changed the font size. 0.5 inches tall is where I started. And so for this, my scale factor is going to be about 2.5 or 5/2. So if you want to represent it as a fraction, it would be 5/2. If you want to represent it as a decimal, it would be 2.5. In part B, it says you are using a magnifying glass that shows the image of an object that is 6 times the factor object's actual size. And then it says the image of a spider seen through this magnifying glass is 13.5 centimeters long. Find the actual length of the spider. So we can set things up similarly here. I can still set up this relationship that I know my scale factor is going to be equal to the magnified spider's length divided by the actual spider's length. And so if I want to try and find this actual length, I can set this up as 6, which is my scale factor. That's what it says, 6 times the object's actual size, is going to equal to 13.5 centimeters divided by whatever the actual length of the spider is, which in this case I'm just calling x. Based on this, I can multiply by x on both sides because I don't want x to be in my denominator. And I get that 6x is equal to 13.5, which means that x is about 2.25, or again as a fraction, 9 over 4. If you didn't set this up as a algebraic equation, you could just say 13.5 divided by 6. That would make sense as well. But I just want to show you this is how you would set it up if you were trying to use algebra to solve this. All right, in part 8, we have this idea known as similarity transformations. And so we're going to talk about this idea of similar figures. And similar figures are going to be the same shape, but usually they're different sizes. So in the bottom, we have two examples here. On the left, similar figures. We have these two diamonds. Let me grab my little laser pointer. So these are the same shape. However, the one on the right clearly is smaller than the one on the left. Congruent figures, which we've talked about a little bit, especially last quarter rather, is something that they're the same size and same shape. And so all of their components are measurably the same. This is what we have here. They are also technically similar figures. So much like a square is always a rectangle, but a rectangle is not always a square, congruent figures are always similar. However, similar figures are not always congruent. And something that we're going to see here in the next slide is that if we're doing more than one transformation to a figure, this is called a composite or a composition of transformations. All right, so we're on number 10 here, and it says that it wants us to graph triangle ABC with the vertices -4, 1, -2, 2, and -2, 1 for A, B, and C respectively, and its image after the similarity transformation. And then it gives us two tasks. It wants us to translate first by this rule given here, xy going to x plus 5, y plus 1. And then it wants us to also dilate xy going to 2x and 2y. So I'm going to start with the translation because that's listed first. But first, let's go ahead and graph our original figure. So I have triangle ABC here at the points that were listed above. In translation, the rules here tell me what to do to the x and y coordinates. And so if I'm going to add 5, if you remember from first quarter, that means going to the right 5 because x increases to the right. And then plus 1 for y means it's going to go up 1 for all of my points because y increases as I go up. So if I was to do that and apply that to all of my points, I'm going to get this new triangle here, which I've labeled as A prime, B prime, and C prime, because I've made one translation here, one transformation. And so originally I was at the point -4, 1. If I go over to the right 5, I'm going to be at +1 for x. And if I go up 1, I will be at +2 for y. So I've slid my shape to the right 5 and up 1, and I can repeat that for each of my points on my triangle. Now, based on what we did in our previous slides, we can take each of those coordinate points and multiply their x and y values by 2, and that's going to give me my final image here once I've done both these. And if I was to do that, I would get a triangle that is clearly larger than the one that I started with. And so just to walk through what that looks like in terms of how do I find these points, well, I'm at the point 1, 2 right now. So if I multiply each of those by 2, I go from 1 to 2, because that's doubling that length along the x. And instead of going up 2, I'm going to go up 4, because that's doubling the length for y. So I've gone from 1, 2 to 2, 4. If I repeat that process for points B and C, so B is at 3, 2, which means C prime rather is at 3, 2. So C double prime should be at 6, 4. So all the way over 6, all the way up 4. And then B prime is at 3, 3. So B double prime should be at 6, 6. All the way over 6, all the way up 6. All right, so I want you to try number 11 on your own. So pause the video and then I will share my solution here in a moment. All right, number 11 says we have these points F, G, and H at the listed XY coordinates. So F is at 1, 2, G is at 4, 4, H is at 2, 0. And we want to do this composite similarity transformation. The reason that these are called similarity transformations and not congruence transformations is we have the same shape, but clearly this triangle is a different size, and that dilation is causing the size change. So let's look at the two things it asks us to do. We have a rotation of 90 degrees about the origin, and if you got stuck or wondering yourself, well, which direction do I rotate? Our default is to rotate counterclockwise. So we're going to go from the first quadrant into the second quadrant. And that's how I remember that's the default, is that's how the quadrants are numbered. I have quadrant 1, 2, 3, and then 4. So that's the default direction for the rotation, is to go in this counterclockwise rotation fashion. All right, let's look at what that would look like after a 90-degree rotation. Here, I'm going to have each of my 3 points has been moved from quadrant 1 to quadrant 2. And so my way of kind of thinking through this is if I was standing on this spot right here in the origin, and if I was to walk 2 steps north and then 1 step to my right, which would be east, then I would land on F. So if I was to do that same thing but just turn to my left first, that means that I would walk 2 steps west and then 1 step north, and that would give me F prime. From the origin, the easiest path for me is to just walk 2 steps to the east, which is where H is. Well, if I was to do that, but having turned left first, I would just walk 2 steps north and land on H prime. And I can do the same thing for G. For me, the easiest way to get there is if I walk 1, 2, 3, 4 steps east, 1, 2, 3, 4 steps north. So I walk out 4 steps, turn to my left, walk out 4 steps. If I was to turn left first before I did anything, and now I'm looking north, and then do those same steps, 1, 2, 3, 4, turn to my left, 1, 2, 3, 4, I land on G prime. So that's my way of doing these 90-degree rotations quickly. If you want to look back at the rules, they should still be available to you in Google Classroom from first quarter. Otherwise, let's go ahead and keep going. Our dilation, this time, it's asking us to shrink our object. That's why our K factor here is less than 1. We have 1/2 for each X and Y. So our scale factor is 1/2. So I should get a triangle that's smaller. So if I take each of these and multiply each of their coordinate points by 1/2, then I'm going to get something that looks like this. F double prime here is going to be at -1, +1/2. H double prime is going to be at 0, 1. And G double prime is going to be at -2, +2. -2 on the X, +2 on the Y. All right, finally, for number 12, it says to describe a similarity transformation that maps quadrilateral PQRS. So that means I'm starting with this one over here on the left that's in blue, to quadrilateral WXYZ. So I'm landing on the green. So I want you to pause and see if you can come up with 2 steps to make this true, taking the blue figure to the green figure. All right, here are a few of the things that I notice, and they don't have to necessarily be in this order, but I noticed that in order to make this blue shape end up over on the same side as the green shape, I definitely need a reflection across the y-axis. So I need to take this and flip it. Right now the point is in that bottom right-hand corner. I want it to be in the bottom left-hand corner. So R is going to end up on Y, S is going to end up on Z, and you can see that in the ordering. P should land on W, Q should land on X, R should land on Y, S should land on Z. So because of that, I know that it's going to be this reflection. I also know that PQRS is significantly larger than WXYZ. And my kind of hint for this is look for things that are on an axis, because those are going to be easier to determine a scale factor with. Because R goes down 1, 2, 3, so R is at 0, -3 right here. And I know R needs to land on Y, and Y is at 0, -1. Well, in order to shrink down from a distance of 3 down to a distance of 1, the scale factor has to be 1/3. And for our purposes, the scale factor is always going to be the same for all of my points in each polygon that I work with. So I can safely assume that that 1/3 is going to apply to all my other values as well. So that means I need, my last thing here is a dilation by a scale factor of 1/3. So these are the 2 things that we need to take this blue figure to the green figure. All right, geometers, I know that was a bit of a longer lesson, but we're done. We made it. We survived. Hopefully you had a fantastic 4-day weekend coming off of President's Day. We have an assignment that is attached to this. It's going to be a homework worksheet. It should be available to you in Google Classroom. If you're in my class, if you're in Mr. Swatala's class, I can't remember if he's using Teams or Classroom, but wherever he hosts your assignments, I assume that it will be in there. So again, thanks for watching the video, and I will catch you in the next one.